Okay, in this lesson we're going to look at some basic probability and probability models. So let's get started. So first some definitions. Okay, so first we have a sample space, and the sample space is the set of all possible outcomes. So for example, if you flip two coins, what possible outcomes could you get on the two flips? So you could get heads on both, first and second. You could get heads the first time, tails the second, or tails the first time, heads the second, or you could get two tails, one on each flip. So this would be considered the sample space. Those are all the possible outcomes. An event. Any outcome or set of outcomes of a random phenomenon. An event is a subset of the sample space. So an example of an event might be the event where we get one tails. So that would be an event. So then you would go back up to your sample space. There are two ways to get just one tails when you flip two coins. So then you can find the probability of getting just one tails. In this case, 2 out of 4, or 50%. Next is a probability model. It's a mathematical description of a random phenomenon consisting of two parts. So you have your sample space, which is a list of all the possible outcomes, and you have a way of assigning the probabilities to those events. So each of those events has a probability associated with it, and you would write that as part of your model. I do think I have an example. Yeah, so if we roll 2 dice and find the sum of the outcomes that appear face up, our probability model would look like this. So up here on the top, these are our possible outcomes, so that's our sample space, 2 through 12. And then these are the probabilities of each of those events occurring. So this whole thing is called our probability model. So two techniques to help you list all the possible outcomes when you're trying to get into your sample space. It's very easy to overlook outcomes, especially if you have lots of them to look at. When it's just like flipping two coins or flipping a coin twice, that's a pretty short list, and so it's usually not too hard. But then when you start adding 3 coins or 4 coins, then it's a little more of a challenge. One way to help you identify how many different outcomes there are and what those outcomes are is by using a tree diagram. So a tree diagram is a list of outcomes that resembles the branches of a tree. So if we do the one with the heads and tails, we had in the first flip, you could get either heads or you could get tails. So that represents our first flip, and you would list those possible outcomes. Now, if you get heads the first time, then you flip the coin again. You could get heads or you could get tails. If you got tails the first time, then when you flip it a second time, you could get heads or you could get tails. And then off to the side, you would list what each of those outcomes are. So we already saw in the previous slide, so you would have heads right here, and you would write HH off to the side. You would have heads, tails, so it would be HT, tails, heads, TH, and tails, TT. So you would list all your possible outcomes, and that would be your sample space. So the tree diagram helps identify what that sample space is. We also have the multiplication rule. So if you can do the first task m ways and the second task n ways, then there are m times n ways to do both tasks. If we look again at the flipping of the coin twice, on the first time you flip the coin, you could get either heads or tails, so you have 2 possible outcomes. So 2 possible outcomes. If you flip it the second time, you could get heads or tails. So again, you have 2 possible outcomes. So then 2 times 2 is 4. You should have 4 possible outcomes in your sample space, which is what we saw on the previous slide and what we saw when we did our tree diagram up here. There are 4 possible outcomes in your sample space. All right. At some point, we're going to be doing some probabilities where we might not put the items that we're taking out back. So knowing whether it's with replacement or without replacement is going to affect what your probability is going to be. So if you're selecting multiple times from a selection of objects and want to find the probability of obtaining one item in the first selection and another item in the second selection, it is important to know if the first item is returned to the list you are selecting from. So total number of choices and the probability depends on whether items were replaced or not. So we have to keep that in mind also when we are doing probability calculations. So we'll see some later, probably more next class than today for this class, but we will be doing some, so start keeping this in mind. All right, so we're going to do a little practice, listing some sample spaces, finding total number of outcomes in a sample space. Page 315, number 40, asks you to identify what the sample space is and then asks another question or two. So again, to help you identify what that sample space is, you could use a tree diagram to get set up. It's going to be very similar to the one we just saw. And then after you've given it a chance, you're going to pause the video, and when you restart, I will show you what that tree diagram should look like. All right, so let's look below here for a tree diagram. So in this case, you were flipping a coin 3 times, or flipping 3 coins. I'd have to look again exactly at how it was worded. But you have a first flip, which is heads or tails, a second flip. So if you had heads the first time, could be heads or tails. If you had tails the first time, you could get heads or tails. And then you have a third flip. So here at the end, this is our sample space. So you could get all 3 heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, and so on. So there are 8 possible outcomes in our sample space. And then you can ask some additional questions like, what's the probability that you get 2 heads out of the 3 flips? So we've got 1, 2, 3 ways to get 2 heads out of 8. So the probability would be 3 over 8. All right, so some basic probability rules. Let's look at these one at a time. So the first one, all probabilities must be a value between 0 and 1. It can be 0, it can be 1, or anything in between. But it cannot go past the 1 or below the 0. So you have to keep that in mind. All probabilities are going to be values inclusively between 0 and 1. Again, it could be 0 or 1, but it can't go past those values outside that range. Okay, second, probability of the sample space is 1. So if you're looking for everything in the sample space, the probability is going to be 1. One of those things is going to happen. If you flip a coin 3 times, you are going to get one of those 8 outcomes. So it's 100% if you're, the probability you're looking for is any of those possible outcomes. The complement. So this C here means complement. What it means is anything that's not A. So if we want the probability of a complement, I want the probability of not getting A. So if I want the probability of not A, that would be 1 minus the probability that I do get A. So 1 minus the probability of A gives me the probability of A complement. Addition rule for disjoint events. We're going to be looking at some other rules. We'll look at the general addition rule for all values, not just the special case of disjoint events. And then we'll also look at some multiplication rules. But the addition rule for disjoint events is if you have two events where A and B are disjoint, disjoint means that they have nothing in common. Anything you find in A, you are not going to find in B. Any outcome you find in B, you are not going to find in A. So then the probability of A or B occurring would just be the sum of those two separate probabilities. Probability of A plus the probability of B would give you the probability of A or B occurring. One thing to note is I also have this term, mutually exclusive. That is synonymous with disjoint. They mean the exact same thing, so I will use them interchangeably, mutually exclusive or disjoint. You need to know both terms and that they are the exact same thing. All right, so just some notation. So we have the union. The union is the set of all outcomes that are either in A or in B or both. Let's go one of these at a time. So you would have A or B, so OR represents the union. Another notation that we use is this U-shaped. Okay, and one way you can remember that that's the notation is that it's the same as the union. So union means you are taking the A group and the B group and you're putting them all together into one big group. And so when we're finding the probability of A or B, you want all of the A, all of the B, and if there's any overlap, you're going to include that as well. The empty event or empty set. This is the event that has no outcomes in it at all. So there's nothing there. So this is a common notation, the 0 with the line through it, to represent the empty set. We don't see that very often, but it is part of the probability in looking at unions and intersections and Venn diagrams and things like that. So we want to keep that in mind. Intersection. So it's the set of all outcomes that are in A and B both at the same time. So you want A and B. So if it's a part of A, it's also a part of B. So it has to be both at the same time. Another notation is this upside down U-looking thing. So the upside down one, the way I remember that is I think about writing an A for and. So writing the capital A, I go up and around, and so that creates this symbol. So this means and. Or you can just remember the union and that the opposite is the intersection. Okay, so this is the notation we use a lot for intersection, and that refers to the and. And then if A and B are disjoint, remember that means they have nothing in common. There's nothing in A that is also in B, and nothing in B that's also in A. They have nothing in common. So A and B would be the empty set. That means they have nothing in common. There's nothing in the joint A and B group. So just some notation there. All right, Venn diagram is a picture that uses a rectangular area to represent the sample space and areas within the rectangle used to represent events. So let me sketch real quick what that looks like. All right, and I'm going to sketch it real quick. It's going to pop up, but then it'll go away. So So a Venn diagram, usually the box represents all possible outcomes. Then you have an event A, then you have an event B. So there's an overlap section, that's the A and B part. And then you also have the parts that are on the outside. Okay, like out in this area. So there could be values that are not in A and not in B, and so those would be included in the outside part of those circles. So that's what a Venn diagram looks like, minus all my scribbles. Okay, so our Venn diagram looks like that. And we'll use some Venn diagrams to help visualize some of our probabilities. So then next, looking at probabilities in a finite sample space, you assign a probability to each individual outcome, must be between 0 and 1, and sum to 1. So these are two characteristics that must be true when you're looking at any probability model of any kind. So we've done a little bit of this before when we were doing normal curves and density curves, and it's very similar. Your probabilities all must be between 0 and 1, and if you take all of the probabilities from the sample space and put them all together, they should sum to 1. And the next thing, the probability of any event is the sum of the probabilities of the outcomes that make up that event. So that just means, if we have when we were doing the 2 coins. So you can either get 0 heads, 1 head, 2 heads in that flipping of 2 coins. If we want to find the probability that the number of heads is less than or equal to 1, that means you have to find the probability that it's equal to 0 plus the probability that it's equal to 1. So if you have multiple events combined describing the event that you're trying to find the probability of, you would just add those events together and that would give you your total probability. And then note, you must check for these 2 characteristics to verify a valid probability. Now what I mean by these 2 characteristics to verify a valid probability are these 2 right here. These are the 2 that you have to check for a valid probability. So you have to check, are all the probabilities between 0 and 1? And do all the probabilities sum to 1? So those are the 2 things that you're checking. The second part isn't something you really check, it's just what you would use and how you would find the probability of an event that combines multiple different outcomes together that make up that event. So I wanted to sketch kind of what a probability model looks like, just so you have an idea. So again, I'm going to put up a screen, and I'll put it up there and then it'll go away. So again, going back to those 2 coins, we're going to let x equal the number of heads when you flip 2 coins. So you always define what the x value represents. Then you would set up your probability model. So x, that represents number of heads, and then the probability of x. So this is our probability model. So number of heads. When I flip 2 coins, I can have 0, 1, or 2. The probability of getting 0 is when you get 2 tails. So that is 1/4 or 0.25. If I have 1 head, so that could be heads tails or tails heads. So that probability is 1/2. And then the two heads, that's just where you get heads the first time and heads the second time. So that probability is 1/4. And then if you add those all up, they would add up to 1. And every single one of those values, the 1/4 and the 1/2, are between 0 and 1. So that is a valid probability model. All right, so if you recall from last class, there was the problem with Betty and Bob's game of heads or tails. And you toss the coin 4 times, you win $1 for heads, lose $1 for tails. Now what you're going to do is try to create a probability model. So you might want to try sketching a tree diagram so that you can get all the different possible outcomes of getting heads and tails, and then use that to help you set up what that probability model would look like. So you'll set up the probability model. Let's see if I can get all the questions on here at the same time. You'll do all the then you'll check, do all the probabilities add up to 1, and is each probability between 0 and 1. Also, on the next slide, I'll try to put both of them up and see how it turns out. Not too bad, I guess. So these are the questions you're answering right now. Okay? Write the probability model and do the probabilities add up to 1, and are each of the probabilities between 0 and 1. Here is the game as it was described in the warm-up from last class. So you'll use this to help set up your probability model with all the probabilities and answer these questions. So pause the video now to do that work, and on the next slide we will check the results. All right, so we'll go to the next slide, see what you should have. All right, so a probability model. So in our case, we're looking at the amount that we win. So x equals the amount won. And these are the possible outcomes. You could gain $4, gain $2, break even, lose $2, or lose $4. So then you calculate each of those probabilities. So getting plus 4 is 1 out of 16. Plus 2 would be 1/4. 0 is 3/8. -2, 1/4, and -4, 1/16. So then you would check all these probabilities would add up to 1. So make your common denominator 16. So 1 out of 16, 4 out of 16, that's 5 out of 16. Plus 6 out of 16, so we're at 11. Plus 4 out of 16 would be 15, and then add another 1 out of 16, you get 16 over 16. So if you add them all up, they do equal 1. I think I did that down here, yep. So see, I rewrote all those probabilities so the denominators were the same. Get 16 over 16, that equals 1. So yes, since all the probabilities add up to 1. And in part C, they wanted to see if each of the probabilities were between 0 and 1. Yes, all of the PX's are between 0 and 1. You could also write it this way. So because part B and part C are true, you can say that it is a valid probability model. So you would sketch your model, you would do the work I did in part B to verify it does add up to 1. You would state that all those probabilities are between 0 and 1, either in words like this or with inequalities like this. And then you can conclude that it is a valid probability model. All right, so a few more probability slides. This one is just talking about setting up probabilities in general. So the bottom number would be all the total possible outcomes in your sample space. And the top number is the count of how many outcomes satisfy event A. So you would add up all those values, how many items are in event A, and put that number over the total in the sample space, and that gives you your probability. So if you have time, here's a few more practice problems. It starts, I think, just a little after page 315. If there isn't any time, I'm going to pause just for a moment before going to the next slide. You can pause the video if you have time to work on these. And so pause now. Okay, if you did not have time to work on those, let's see, how many more slides do I have? Yeah, I thought I was going to press the end. All right, so now we're going to look real quick at a multiplication rule. Two events A and B are independent if knowing that one occurring does not change the probability of the other occurring. So like if you flip a coin and you get heads, if you flip the coin again, that second flip isn't dependent on what your first flip was. It's not going to change the outcome of the second event. So our multiplication rule for independent events, again, this is a special case. The independence is a special case. If A and B are independent, you have to have this condition first. Then you can just take the probability of A times the probability of B to find the probability of A and B happening at the same time. So you can only multiply the individual A and B if the two events are independent. And then we'll discuss later about what to do when they're not independent. So just make sure that it is stated A and B are independent before you multiply those two probabilities together. One thing I want to note here is that something being disjoint and something being independent are not the same thing. They are two totally different things. So it's important that we know the difference. So when I get back to class, make sure we spend some time discussing examples of something that's disjoint that might be independent and something that's disjoint that is not independent, and vice versa. The independence part, whether it's independent or not independent, being disjoint. So one thing to note is if you're dealing with disjoint, the only time we deal with disjoint is if the question being asked is an or question, the probability of A or B occurring, which always refers to adding probabilities together. If we're dealing with independence, then we're dealing with an and kind of question. That's this example up here. So you want the probability of A and B happening at the same time. When we have those kinds of probabilities, we are using a multiplication operation to find the probability that we're looking for. So just by the nature of the question being asked, these are not the same thing. So make sure that you keep that in mind. I have students that get those two things confused all the time, so we will work on that some more. And then that was my last slide, so if the sub could check the notes that I left and write the homework on the board for you. You can spend whatever time is left on those problems, and then we will go over them in class next time.